those states are automatically satisfied. Those conditions are automatically satisfied. So if we only ask about the lowest pressure trajectory, it's the physical state conditions sort of trivialize, except for the mass shell condition. So the mass shell condition is just given by the correction to the Hamiltonian. So the shift in the mass squared for a closed string at first order is given by 2 over alpha prime times the shift in the world sheet Hamiltonian on a circle of circumference 2 pi. And the shift in mass squared of an open string at first order is just given by half that value on an interval of length pi. And the shift in the world sheet energy is given by the usual first order perturbative formula. So nothing exotic there. Question, by the way, any questions so far?
I'm a little confused about the CFT structure of this 2D theory that you wrote down.
I was thinking after gauge fixing. So
yes.
We're going to gauge fix now.
So
after gauge fixing, we have just a conformal field, an ordinary conformal field theory of D equals central charge 26. Well,
and this denominator is not. I mean, it's actually a Lagrangian which has this funny term, and that's okay. But it's okay.
It's a conformal field theory we're only going to treat as an asymptotic expansion when the string is large. So that denominator is always, or let's say almost always, non-zero and large. So we're always going to quantize the theory in states where the conformal invariance is very strongly spontaneously open. So the denominator is big and so forth. There are some complications because for rotating strings, the denominator actually becomes small at the boundary, and we're going to have to deal with that. But yeah, treating the theory in this kind of asymptotic expansion seems to be a legitimate thing. And in fact, that's sort of the core of how one treats these theories at large.
Is there some understanding of the full set of classical solutions to this action before you, or just the solutions at large x somehow?
We're only looking at solutions at large x, and even the full set. I mean, it's just anything a relativistic rotating string can do, as long as its curvatures are small and its length is large, and its curvatures don't even have to be small everywhere. It can have localized curvature singularities, and I'm going to show you in some examples how we deal with those. In some examples, we don't know how to deal with them. So yeah. So it's an interesting thing to look at. By the way, so for people who know all about supersymmetry and supersymmetric moduli spaces, this is actually a very familiar type of effective action. You also have these things in denominators, but the denominators are sort of non-derivative functions of moduli. Right? You have effective actions on moduli space where the moduli, the undifferentiated moduli, go into the denominator. It's the same sort of thing, but there it's only scale invariance and not Lorentz invariance that's spontaneously broken. Here, Lorentz invariance is actually spontaneously broken. Two-dimensional Lorentz invariance is spontaneously broken as well, so the gradients can get at that as well.
So just one more question. Let's say I forgot about the time lag direction and I wrote down this action for a single scalar. I can do that formally, right?
We're actually going to look at an example. In the second half, we're going to come to an example where one does.
And that's some understood CFT.
It's understood. You're going to understand it by the end of this. So we're going to. So in the second half, we're going to analyze the O2 model and the cubic supermodel in 3 dimensions both. And in those cases, things are going to be reduced to a single Goldstone at large J, and it will have a Lagrangian very much like this, but with only one.
Is there any other scale apart from the string scale?
No. So in a minute, we're going to introduce a regulator scale to regulate certain singularities, but that scale is sort of artificial.
But when you say small string versus big string, what do you mean?
I mean it's big compared to the string scale, yeah. Okay, so now let's actually evaluate this thing. So in general, this first order shifting energy is given by two pieces, the Casimir energy, plus the classical value of the interaction Hamiltonian in the classical rotating solutions with the given quantum numbers. So, and here's a fact about classical mechanics you may or may not know, but this is just always true in classical mechanics, that the classical value of the perturbing Hamiltonian is equal to the negative of the classical value of the perturbing Lagrangian in the lowest state with given quantum, with given conserved global quantum numbers. That's a completely general fact about classical mechanics. You can show it using action-angle variables or complicated Legendre transformations, but it's just some fact. It's the generalization of the fact that the state of lowest energy is always static. So, no higher loops or even one loop diagrams involving interaction vertices contribute at next domain order. So each additional interaction vertex and each individual loop is suppressed by additional powers. So quantum corrections are actually very simple here. The only quantum thing here really is the Casimir energy. So that's the beautiful thing about working in conformal gauge. All the quantum effects which would ordinarily be present in the measure we've pushed into this explicit anomaly term. So now let's see how this works for open strings in conformal gauge. We'll see it doesn't work very well. It works very badly. But then we'll understand why. So the solution to the lowest lying state with given angular momentum J in a single plane is linear. So the time-like coordinate is linear, and the complex coordinate in the plane of rotation has this this helical dependence on world sheet time. So by helical, I mean it's invariant under a combined shift in time and rotation symmetry transformation of Z. So the whole solution is invariant under this helical symmetry. And again, this is a completely general fact about classical mechanics. So if you have a theory with a global symmetry, the lowest solution, the lowest classical solution with given quantum numbers is always invariant under helical symmetry. But unfortunately now, so we have our classical solution, we have our formula for evaluating the energy shift in terms of the classical solution, but unfortunately our analysis breaks down in its own terms. The Lagrangian is singular near the endpoints, and it's a non-integrable singularity. So it's just a divergent integral of the anomaly term. So it's all the fault of this anomaly term. It diverges like this. And you can't get rid of the anomaly term because it's just there. You need it for consistent quantization, so it looks like a disaster, and you don't know what to do. So this happens actually both in the open string and the closed string. So for the open string, the singularity is present because the boundary is moving at the speed of light. The closed string, the singularity is present because there's a fold. And in both cases, the anomaly term diverges. So let's consider the first. So first, let's consider a model calculation where there is no singularity. So the breakdown is a short distance singularity, and it can be removed by renormalization. But we can consider a simpler case where the singularity isn't there at all. So if we consider closed strings in 5 or more dimensions, we can let the string rotate in 2 different planes simultaneously. And in that case, for generic angular momenta in 2 planes, there's no singularity at all. The solution is just smooth. So the classical solution looks like this. Again, there's a helical symmetry. The amplitudes of rotation are given by the square roots of the angular momenta with these funny signs. Signs are important. And now the denominator is just never vanishing, and the Lagrangian density is 5. So for generic biplanar angular momenta, the energy looks like the mass squared of a closed string has a classical piece, it has a Casimir piece, and it has this anomaly piece that is explicitly proportional to 26 minus d, and it's symmetric in the 2 angular momenta, and you can see that it becomes singular when either of the 2 angular momenta vanishes. So when we squeeze the rotation into a single I'll explain why later. When I show you the case we do understand how to renormalize, you'll see why the closed string is a little harder. But so since we don't understand that, so I was just showing you this model calculation to explain, that there's nothing, you can decouple the issues of anomalies and consistent quantization and so on from the issue of these singularities. They're really separate issues. And for effective strings in 5 and higher dimensions, there don't have to be any singularities at all for closed strings. Questions so far? Okay, so let's forget closed strings now, and just return to our focus on open strings with Neumann boundary conditions, and we're going to regulate and renormalize the boundary singularities in the standard way. And this works fine because the UV divergences are just local terms, and local at the boundary in particular. So the classical solution, again, it has some simple explicit form. The only slightly interesting thing is now the second Fourier mode on the string is excited as well as the first. That's different in the open string case versus the closed string case. I don't know. This is some interesting thing. The amplitudes of rotation have some slightly different powers of 2 in them. But so now we're going to first regularize the singularity. So we're going to change our choice of this composite operator purple phi in order to remove the divergent energy while still preserving all of the symmetry. So we're preserve diff times vio exactly, but smooth out the singularity. So we just add this extra term. So now I'll start using this notation xpq, where that's just the bilinear of p left moving and q right moving derivatives on the coordinates. And then this hatted x22 is a Weyl covariantized version of the unhatted x22. So it's just something, and it's in particular it's non-singular everywhere, especially at the boundary. It's just non-zero and smooth, and so the singularity in the anomaly term was just had to do with the vanishing of this thing inside the log, and now it doesn't vanish because we've cut off the singularity with some scale epsilon. So there are a huge number of terms that don't contribute that let's throw out for right now. And you see that the Lagrangian density in the regulated theory just looks like modulo those non-contributing terms. It looks like beta over 2 pi times x12, x21 over x11 squared plus this extra term proportional to epsilon to a quarter alpha prime x22. So it's really just the original Polchinski-Strominger anomaly term with this extra term here, plus a lot of terms that are 0. So notice that whenever and wherever, so this term is only important at the boundary. Whenever and wherever x11 is non-vanishing, when we take j large, x gets large, so that this thing up here goes as j squared, this goes as j squared, and this only goes as j. So if x11 is non-vanishing, this is negligible even if epsilon is finite. It's only at the boundary that this regulator is important at large j. So now let's look at the divergence when we take epsilon to 0. So the integral, so the mass shift, goes like delta m squared goes as 1 over epsilon 26 minus d over 24 alpha prime times this very funny particular combination of angular momenta. It's exactly j1 plus 8j2 to the 1/4 power. Wow, that's weird. We saw this and we thought it was very strange because we sort of took a year off because we thought we made some dumb mistake. But it turns out it's not a mistake, it's actually true. There's a unique counter term. So, so the analysis of boundary counter terms is something that is interesting. I may not have time to really get into it, but the rule is that boundary counter terms are dressed with, so the only operator that appears to fractional or negative powers is this x22. Boundary operators are always dressed with that times the monomials and all the other derivatives. And there's a unique counter term satisfying that dressing rule that is marginal and scales with non-negative J scaling. And it's this operator x22 to the plus 1/4 power. And that operator, when you evaluate in the classical solution, is exactly this, has exactly this dependence, J1 plus J2 to the 1/4 power. So you can remove this divergence just by adding this boundary counter term with the appropriate power. So this is important. So if there are questions on that, please ask. It may be something that I can answer later, but maybe not, so.
So what if we instead had QCD? Why does it have to complete to a microscopic string theory?
It doesn't.
What's the microscopic string theory for QCD?
Oh, I mean, whatever is the holographic, the world two theory of the holographic dual trivial QCD.
Okay.
But I mean, we don't know what it is.
Okay.
But we know it's something, or at least we believe it's something. Right? The planar QCD is described by world two theory. That's not a controversial.
Yeah, sure, but why does the UV completion have to take the form of the string theory? Why couldn't it just be some form of the
Sorry, we're talking about world two completion of the two-dimensional theory, not four-dimensional theory. Four-dimensional theories in the planar limit have string duals. That's what I mean by UV completion. But it doesn't depend at all on the nature of the completion. It will probably be true for any unitary theory that completes it, but at the moment we're trying to understand how general it is. But yeah. So after renormalization, we find that again we have this same structure with a classical piece and a Casimir term, and then this anomaly term, which is given by this complicated function of J, but this whole thing scales as J to the 0, and it's finite. And then there's some ordered, corrections that are too small to care about. We've thrown them out, coming from higher loops and higher dimension operators and things. Now, what's interesting is that for angular momenta lying in a single plane, the D dependence drops out, and we get exactly the same value as in the critical dimension. There's probably some profound explanation for that fact, but we don't know what it is actually. Maybe it's profound, maybe it's boring, but we don't know it. It's just something that comes out of the explicit factoid. And by the way, there's a term I left out, which I couldn't have included, which is this quark mass term, J1 plus J2 to the 1/4 power, with a finite coefficient. Of course, we renormalized the infinite piece, but we could have added, a finite term proportional to the same operator. And generically, we certainly expect that to be there, because it's known that adding putting a massive quark on the string endpoint at the leading large J effect is exactly that term with the finite coefficient. Now, in real QCD, so this is sort of the the large J version of the string dual of bosonic QCD. But in real QCD, there are certainly additional degrees of freedom at the endpoint carrying spin and flavor. So this is work in progress with my collaborators. But these degrees of freedom constrain the allowed operators. Since chiral symmetry forbids quark masses, we expect that the J to the 1/4 term is constrained in terms of a soft pion amplitude. But at the moment, we don't understand quite how to realize these degrees of freedom carrying chiral symmetry. So this is a general prediction, but we haven't implemented it yet. So now I was going to talk about this dressing rule, and maybe I'll come back to it, but I'm running a little bit behind, and I'd like to talk about our more recent examples. So let me actually sort of skip over the dressing rule, and just summarize what we learned about the world chief conformal field theory at large J. So we found that the effective string theory framework is predictive for large J corrections. For closed strings and for closed strings in D equals 4 and open strings in any dimension. The leading corrections are this mass shift that goes as J to the 1/4 with a non-universal coefficient. And they're associated with localized terms at boundaries and folds. But the asymptotic intercept, the J to the 0 term, is calculable modulo this quark mass complication. So this is interesting. So it's showing that even though we know really nothing at all about the world sheet conformal field theory except massless degrees of freedom and symmetries and so on, there are things that we can actually predict and actually calculate, and that are phenomenologically relevant and testable. And the same is true of every other amplitude, so up to and including relative order J to the -1, the only non-universal coefficient is this quark mass term. So you can calculate all sorts of things at that order, photon emission and so forth, from strings of large J, photon emission, pion emission. So this is an interesting framework to develop. But the striking thing is that at large quantum number, the world sheet theory simplifies so much you need to know almost nothing about the theory. And so that should be a more general principle. There's nothing magical about the world sheet theory of the QCD string. So let's try to understand the lesson and what else we could learn with it. So we can't offer some grandiose theory of how it works, but we'd like to sort of look at some previously non-understood, strongly coupled conformal field theories. And since none of that discussion had much to do intrinsically with 2 dimensions, let's look at some 3-dimensional examples. So the most famous example, I think, is the of a strongly coupled theory with a global symmetry that we don't have many tools to solve, other than maybe Bootstrap, is the critical point of the O2 model in 3 dimensions. And we could also add supersymmetry, so there's a closely related theory where one adds n equals 2 supersymmetry and looks at the supersymmetric theory of a single Kagel superfield with Q single potential in 3 dimensions. It also flows to a fixed point. Right, so the simplest possible question about the supersymmetric example, I think I'll ask, because especially for this audience, it will hopefully get a reaction. So I'd like to poll people and sort of ask if anyone is willing to stick their neck out and predict the anomalous dimension of the lowest operator with R charge J, namely phi to the J. And if I told you the answer already, please don't ruin it for everyone else. But there's so many smart people in the room who work on localization and highly mathematical supersymmetric theories. In fact, that's what it means to be a smart person. So I'm sure all you smart people can definitely answer this simple question about the simplest possible n equals 2 theory of 3 dimensions. If you had to guess, how would you guess this this anomalous dimension scales at large J?
Linearly.
Linearly in J.
One by J.
I think Abhijit said linearly, and then maybe Subrat
I
said
said
something.
inversely.
Sorry?
Inversely.
Inversely? No, that's inconsistent with unitarity.
Is it?
The unitarity bound has to be bigger than 1/2, I think, in 3 dimensions.
The anomalous dimension has to be bigger than 1/2.
The dimension altogether has to be.
So what do you mean by anomalous?
Oh, sorry. Yeah, let's say the total limit. Oh, I see.
Total dimension. No, I don't mean total dimension. I
You're,
mean,
you're predicting that this thing goes as
Anomalous.
dimension 1/2 plus 1 over J or something.
Okay.
That's a very crackpot idea, which is completely wrong. That's at least brilliant. But yeah, so all the smart people I talked to, including the smartest person, all made the same prediction as yourself. Well, since I'm on video, I'll say it wasn't quite a prediction, it was a strong suggestion of plausibility. Sorry. But everyone basically said, all the smart people basically said either linearly or linearly plus small corrections. So maybe j plus, plus 1 over j or something like that. But, well. Because everyone always does say that. And for the record, I'm not trying to say that we were smarter than the smart people. We thought so too. We actually spent a long time trying to prove that result. But we couldn't because it's wrong. The actual scaling turns out to be j to the 3 halves. So the actual lowest state lies far above the BPS bound, and supersymmetry is very, very strongly broken, parametrically strongly broken in the large j set. And the scaling in the O2 model is the same. Scaling in the O2 model is the same. So the dimension of the lowest operator with charge j scales as delta sub j goes as j to the 3 halves at large j. And by the way, many of you probably also know this is the same scaling as relativistic free fermions in 3 dimensions. So basically in 3 dimensions, not everything, but almost everything scales as j to the 3 halves. And by everything, I mean the dimension of the lowest operator with charge j under some exactly conserved global symmetry.
But not free scalars.
But not free scalars, right. So what's the explanation and why doesn't it always apply? That's sort of the question that led us into this general analysis. So, okay, so in fact, I can say some simple things before going deep into the renormalization group analysis that will tell you how to answer these questions. So,
Sorry, Simeon, phi was real or complex?
Complex. That's why it carries a global. I mean, in the supersymmetric version, it has to be complex.
So this is n equals to 2, right?
Yeah. But the only symmetry in that theory is the R charge. And in O2, it's not. There's a supersymmetry, also complex scale. But in fact, in retrospect, we realized that all of these large J scalings for these theories can all be predicted just on the grounds of dimensional analysis, and J to the 3 halves is more or less automatic. Because at large J, the lowest state has a homogeneous energy density and a homogeneous charge density. So on the sphere, the only scale invariant relationship between the two is that. It's the only thing you can possibly write down if the curvature of the sphere is irrelevant. And the curvature of the sphere is irrelevant if conformal field theory has good spectra on flat slices. So if you quantize the theory on the torus and it still has a good spectrum, that means that the curvature is irrelevant. The curvature is not supporting the spectrum. So what are the theories that have good spectra on flat slices? So free fermions, the O2 model, yes, free fermions, the O2 model, the cubic Sigma model, basically everything, non-SUSY Chern-Simons matter theory, non-SUSY QED, all these things, have conformal fixed points. Even n equals 1 versions of these things, the CPN model, not just O2, but the ON model. So basically everything, almost everything, has good discrete spectra on the torus. Things that don't are free scalar and n equals 2, the supersymmetric theories with moduli. Or n greater than or equal to 2 theories with moduli. So these theories have exact flat directions. They don't have good spectra